When we think about mega engineering, our minds usually jump straight to a single, like, monolithic object, a towering skyscraper or, I don't know, a massive suspension bridge, right?
Yeah, exactly. It's usually a localized event, like a single focal point.
Right. You pour the foundation, you stack the steel, and, well, after a few years of concentrated effort, it's done.
Right. It's finished.
But when you look at the institutional data on global energy infrastructure right now, that whole skyscraper metaphor just completely disintegrates.
It really does. It falls apart.
Yeah, because we're not looking at a single building here. We're looking at an entire, sprawling, continuous assembly line of the most complex machines on Earth. And it's operating on a scale that honestly defies easy comprehension.
I mean, it is the absolute definition of a rolling industrial juggernaut.
It really is. So welcome to this deep dive into the China Nuclear Builds weekly update, specifically for the week ending July 19, 2026.
Glad to be here. There's a lot to cover.
There is. And our mission today is to unpack this stack of institutional research on uranium and nuclear power. We're cross-referencing sources like World Nuclear News, NUCNet, and the IAEA PRIS database.
Right, the gold standard for this kind of tracking.
Exactly. And the goal is to understand the sheer unprecedented scale of China's current nuclear expansion. Because whether you're tracking global energy transitions or you're just insanely curious about mega engineering, this is happening right now.
Yeah, right in front of us.
And it represents roughly half of all global nuclear construction. Half.
Half. I mean, it's the statistic that forces you to just recalibrate your entire understanding of the global energy market.
Seriously.
So to truly set the stage for you, let's lay out the fleet-level numbers as they stand right now in mid-July 2026.
Okay, let's hear it.
So China currently operates 64 reactors actively connected to their national grid. That gives them an installed capacity of roughly 63 to 64 gigawatts electric, or GW.
Which is, I mean, that's already a massive fleet by any international standard.
It is, yeah. But the staggering figure is the forward pipeline. They have approximately 36 reactors currently under construction.
36?
36. And they're spread simultaneously across 19 different sites.
Wow.
Yeah. And when those 36 reactors are finished, they will add an estimated 38 to 43 GW of additional capacity.
Okay, let's unpack this for a second, because you don't just wake up and accidentally orchestrate 19 concurrent nuclear mega projects. I mean, this is a highly deliberate mobilization.
Precisely. And there is this really striking comparative fact from the sources that you need to keep in mind to understand the momentum here.
Okay, what is it?
The average age of China's operating nuclear units is less than 12 years.
Oh, wow. Less than 12 years.
Less than 12. In fact, roughly half of their fleet is under 10 years old.
That is incredibly young for a nuclear fleet.
Right, because if you look at the global average age for a nuclear reactor today, it's hovering around 32 years.
So we are looking at a fundamentally young, modernized fleet. But how does this specific week's data fit into their broader strategy? Because building 36 reactors at the same time requires a bottomless well of capital and labor.
It does, and it all ties back to the 15th five-year plan.
Right.
Which covers 2026 through 2030, and that was officially approved back in March of 2026. The target they have codified is to reach 110 GWs of installed nuclear capacity by the year 2030.
110 GW.
Yeah. And to hit that number, they need a 76% increase from the 62 GW of operating capacity they had at the end of 2025.
A 76% capacity increase in just 5 years. I mean, that is wild.
Just an aggressive timeline.
Right. And it means we have to look closely at what is crossing the finish line right now to understand the mechanics of how they actually plan to hit that target. Which brings us to the biggest update from this week's research.
Right, the new milestones.
Yeah, let's talk about Changjiang Unit 3 down in Hainan Province. The tracking shows this reactor achieved first criticality on July 10, 2026.
Yes, a major step for that Hualong 1 unit.
But, for those tracking the financial and revenue side of these projects who might blur the engineering jargon, can you explain first criticality? Because it's different from a revenue-generating grid connection, right?
It is a really critical distinction, yeah. From an engineering standpoint, achieving first criticality means you have successfully initiated a self-sustaining nuclear chain reaction.
Okay. So the engine is on.
Exactly. The control rods have been carefully withdrawn just enough that the neutron flux is stable, the core is alive, it's generating heat, and the physics are behaving exactly as modeled.
But it's not making money yet.
Right. It's not making money, and it's not pushing electricity to the public.
So what is it doing?
The reactor is essentially idling. Engineers are running low-power physics tests, verifying the thermal hydraulics, checking the primary coolant pumps, and just ensuring every safety system responds perfectly to real-world thermal stress.
Got it. Which explains why it can take weeks or even months between that first criticality milestone and the moment they actually flip the switch.
Yeah. Exactly. You have to run through all the tests first.
Right. Now, speaking of flipping the switch, the reporting from World Nuclear News notes that just a few days before Changjiang's milestone, on July 4th, Taipingling Unit 2 over in Guangdong achieved its first grid connection.
Yes. And that is the revenue-generating milestone.
Right.
Taipingling Unit 2 is also a Hualong 1 reactor. And grid connection means the reactor steam has actually spun the turbine, the generator has synchronized its frequency perfectly with the national power grid, and it is actively exporting megawatts.
It's huge.
Yeah, and following its current commissioning tests, it is expected to enter full commercial operation in the second half of 2026.
And once it's running at its full base load capacity, that single unit will generate over 9 billion kilowatt hours annually.
9 billion.
Just massive.
Uh.
And looking at the broader data set, the class of 2026 has been operating on a relentless drumbeat.
It really had.
Because we've already seen commercial operations begin at Zhangzhou Unit 2 on January 1st,
Yeah.
Taipingling Unit 1 on April 19th, and Sanao Unit 1 on April 29th. But I want to pause on Sanao Unit 1 because the funding mechanics here are really intriguing.
Oh, it is a massive shift. Beyond the engineering achievement, Sanao represents a fundamental evolution in how these projects are capitalized.
How so?
Well, it is the very first Chinese nuclear power project to involve private capital. Geely Technology Group holds a 2% equity stake in it.
A private automotive and technology group buying into a nuclear plant.
Yeah.
I mean, 2% might sound small on paper, but in the context of historically state-dominated infrastructure, why open the door to private equity now?
Because of that 110 GeWe target we mentioned earlier.
Ah, right. It's too big.
Exactly. When you are scaling up 36 reactors simultaneously, the capital expenditure is just astronomical.
Right.
So by introducing private equity, even at low single-digit percentages, they are diversifying the risk and testing a completely new financing model.
Okay, that makes sense.
Yeah, it proves that the domestic financial markets view these nuclear plants as stable, long-term, revenue-generating assets, not just state-subsidized science projects.
That makes a ton of sense. You secure the capital, you feed the pipeline. But, to achieve these finish line moments, you need an absolute army of projects moving through the mid-stages of construction.
You do. The assembly line never stops.
Right. So let's move from the reactors powering up today to the logistical choreography of the megastructures currently being built.
Yeah.
Because nothing illustrates this mid-construction phase better than the containment dome installations.
Oh, absolutely. It is arguably the most critical transition point in a reactor's construction timeline.
And NUCNET's recent tracking highlights Lianjiang Unit 1 in Guangdong. In early June 2026, they hoisted the outer containment dome into place.
Right.
And for context, this steel structure is 41 meters in diameter and weighs roughly 1,000 tons. Now, I often hear this compared to lifting an office building, but that doesn't really capture the engineering reality, does it?
No, it really doesn't.
Because you aren't just lifting dead weight. You have to perfectly align a 1,000-ton steel lid onto a concrete cylinder with, millimeter tolerances.
Exactly. It is an orchestration of heavy logistics and atmospheric physics. You need the world's largest crawler cranes, these massive machines that have to be assembled on-site just to do this one lift.
Just for the one lift.
Yeah. And you can only execute the hoist within very specific narrow windows of low wind speed.
Oh, because of the wind catching it.
Right. If a gust catches a 41-meter-wide steel dome, it acts like a giant sail.
Yeah, a 1,000-ton pendulum is not something you want swinging over a nuclear island.
Definitely not. And beyond the spectacle of it, capping the reactor building fundamentally shifts the nature of the work.
How so?
Well, you are transitioning from heavy civil engineering, so pouring millions of cubic meters of concrete, tying rebar, dealing with weather delays, and moving into clean, high-precision mechanical installation.
So once the dome is sealed, the environment is controlled enough to start bringing in the hypersensitive components.
Precisely. That is when they install the reactor pressure vessel, drop in the steam generators, and begin the really complex welding of the primary circulation piping. And the sheer volume of these lifts is staggering right now. In February, Haiyang Unit 4 had its steel dome hoisted. Around the same time, Zudapu Unit 1 installed its 820-ton inner steel dome.
Right.
And over the summer, Lufeng Units 1 and 2 had their massive steel containment rings locked into place.
Which brings up a huge logistical question for me. How are they achieving this concurrent drumbeat? Is it regionalized supply chains? Because you can't just have, like, one crew of specialized welders traveling to 19 different sites.
No, you couldn't possibly. It is a combination of localized supply chains and extreme modularization.
Modularization. Okay.
Yeah, they aren't building these reactors stick by stick on site. Entire subassemblies are manufactured in specialized factories, shipped by heavy barges, and then assembled on site like a massive precision machine puzzle.
So they just lock it together.
Exactly. This modular approach allows for parallel work streams, which drastically cuts down the on-site timeline.
Okay, so we have the finish line and the mid-construction heavy lifts. But to sustain a pipeline aiming for 110 GWE, you have to constantly feed the front end.
You do?
And the PRIA's database and recent research show a flurry of projects that have just poured their first nuclear safety-related concrete in 2026.
Right, the newest batch.
Yeah, we are talking about Taipingling Unit 4 in May, Jinkomen Unit 2 in April, and Zhuhai Unit 1 in January.
And we really need to look at the master plan for a greenfield site like Jinkomen.
Okay, what's happening there?
Located near Ningbo, they are currently pouring concrete for the early units, but the site is ultimately designed to host 6 Hualong 1 reactors.
6 gigawatt-scale units at one site.
Yes. When all 6 are completed and running at full capacity, that single site will generate around 55 terawatt-hours, or TWH, of electricity annually.
That is just hard to visualize.
To put that in perspective for you,
Yeah.
55 TWH equals half of the entire city of Ningbo's total electricity consumption for the year 2024.
Wait, really?
Yeah. You are talking about replacing the baseload power for half of a massive, globally significant industrial port city with a single localized facility.
That is unbelievable. And they are aggressively securing the future pipeline too, right? To ensure that manufacturing capacity doesn't sit idle.
Exactly. In April 2025, the State Council approved a batch of 10 additional reactors across 5 different sites.
Right, I saw that.
So that's Fengchenggang Phase 3, Haiyang Phase 3, Sanmen Phase 3, Taishan Phase 2, and Shapu Phase 1.
And the numbers attached to that approval are staggering. That single batch represents an estimated investment of 200 billion Chinese yuan, which translates to roughly 27.4 billion US dollars waiting in the wings.
It's a massive influx of capital.
It is. But it makes me wonder, is capital the only bottleneck here? With 36 reactors under construction, I think the natural assumption from a manufacturing standpoint is that you would just standardize on a single hyper-reliable design.
Right, that would be the conventional wisdom.
Yeah, because if you want speed, you print widgets. You copy and paste one blueprint. But digging into the sources, we see a highly diverse technological strategy.
It is incredibly diverse. Now, you are right that there is a dominant design. The domestically developed Hualong 1, also known as the HPR 1000, is the undisputed workhorse.
Right.
You see it being deployed heavily at sites like Zhangzhou, which is currently being built out to be the world's largest Hualong 1 base. But they're also deploying the CAP 1000 in heavy numbers.
And the CAP 1000, just to clarify, is their indigenous adaptation of the American Westinghouse AP 1000 pressurized water reactor, correct?
That's right. They are building CAP 1000 fleets at major sites like Sanmen, Haiyang, Lianjiang, Jidapu, Beilong, and Lufeng.
Okay, I have to push back here. From assembly line perspective, doesn't running multiple different gigawatt-scale reactor designs just, well, kill your efficiency?
How do you mean?
Well, you need different supply chains for valves, different training simulators for operators, different licensing reviews. Wouldn't it be massively faster and cheaper to just pick the Hualong 1 and standardize the entire supply chain?
From a pure short-term accounting perspective, yes. Standardization drives down unit costs. But energy infrastructure on a national scale is about long-term resilience and strategic capability.
Okay.
By pursuing parallel pathways, so scaling up both the Hualong 1 and the CP 1000 simultaneously, they ensure they are not vulnerable to a single supply chain bottleneck.
Ah, I see. So if there is a manufacturing delay for a specific Hualong 1 coolant pump, the CAP 1000 sites just keep moving.
Exactly. Furthermore, it protects the fleet against generic design defects. If an unexpected issue forces you to throttle back one reactor type, your grid doesn't completely collapse.
That's a really good point.
Yeah. And more importantly, it keeps their domestic manufacturing base sharp across multiple types of pressurized water reactors, providing a foundation to pour resources into next-generation technology.
And here's where it gets really interesting.
Right.
Because this next-generation tech isn't just, theoretical research papers. It is being built right now.
It is.
I want to talk about the Zhuhai project in Jiangsu province. We noted they just poured first concrete there in January 2026.
Yeah, the Zhuhai project is arguably the most innovative industrial site in their entire pipeline. It is an absolute world first.
Right.
They are taking standard pressurized water reactors, 2 Halong 1 units, and integrating them directly with a high-temperature gas-cooled reactor, or HTGR.
I have to admit genuine confusion here. How does a hybrid plant actually work mechanically?
It's unique, for sure.
Yeah, like why would you plumb a standard water reactor together with a gas-cooled reactor?
Yeah.
What is the actual advantage there?
It comes down to the physics of heat and the specific needs of the end user. Zhuhai is designed for the world's first large-scale integration of nuclear energy directly into the petrochemical industry.
Okay.
Petrochemical cracking and refining require massive amounts of extremely hot industrial steam. A standard pressurized water reactor tops out around 300 degrees Celsius.
Right.
That is great for spinning a turbine to make electricity, but it is not hot enough for heavy chemical processing.
So traditionally, a petrochemical plant has to burn massive amounts of coal or natural gas just to generate that high-grade heat.
Exactly. But a high-temperature gas-cooled reactor uses helium gas instead of water as its primary coolant, and graphite as a moderator.
Helium, okay.
Yeah, and because helium is an inert gas, it doesn't boil. This allows the HTGR to operate at temperatures exceeding 700 degrees Celsius.
Wow. So they are using the Halong 1 units for baseload electricity and tapping the HTGR specifically to deliver that 700-degree heat directly to the chemical plants.
You've got it. The HTGR at Zhuhai is designed to supply 32.5 million tons of industrial steam annually straight to the petrochemical facilities.
That is wild.
By replacing the heat source with a nuclear reactor, the project is engineered to replace 7.26 million tons of standard coal every single year.
Every single year.
Yeah, it is a massive mechanical leap forward for decarbonizing heavy industry beyond just the electrical grid.
That is fascinating. The physics dictate the application. And the technological diversity doesn't stop with gas reactors.
No, it doesn't.
The sources detail the CFR 600 reactors currently under construction at the Jiapu site in Fujian province. These aren't water or gas reactors. They are sodium-cooled fast reactors.
Yes. Jiapu is a strategically vital demonstration site for their Generation IV ambitions.
How so?
Well, fast reactors operate on completely different mechanical principles than standard commercial reactors. In a standard reactor, you use water to slow down the neutrons so they can split uranium-235.
Right.
But a fast reactor uses liquid sodium as a coolant, which doesn't slow the neutrons down.
So the neutrons are moving much faster, which changes how they interact with the fuel.
Precisely. Fast neutrons can interact with uranium-238, which makes up the vast majority of natural uranium, but is normally useless in a standard reactor.
Okay.
This allows fast reactors to essentially breed more fuel than they consume, and even burn up long-lived nuclear waste from older reactors.
But you can't just plug standard fuel rods into a machine like that, right?
No, you can't. And that is what proves they are playing a very long, highly coordinated game here. China is simultaneously building the complex back-end fuel cycle infrastructure required to support these fast reactors.
Okay, where is that happening?
At an industrial park in Gansu, they are constructing a pilot reprocessing plant rated at 200 tons per year, right alongside a facility to fabricate mixed oxide, or MOX, fuel.
So they are extracting the usable isotopes from spent fuel and blending it into MOX fuel to feed the fast reactors at Jiapu.
Exactly. They aren't just building a new type of power plant, they are mechanically constructing an entirely closed-loop nuclear ecosystem.
That is just next-level planning. Now, before we wrap up, I want to touch on one more technology mentioned in the research, the ACP-100, better known as the Linglong one.
Ah, yes.
It's a small modular reactor, or SMR, located down at the Changjiang site. The tracking data shows it completed a non-nuclear turbine test back in January 2026.
It did, but this is where we have to be incredibly rigorous about how we interpret institutional data.
Right, because the nuclear industry globally is famous for ambitious timelines and projected commercial dates.
Exactly. There is always a difference between a press release and actual grid connection.
Yeah.
While the Linglong one has been highly anticipated, if we look at the IAEA's PRIS database, which, as we know, remains the global gold standard for objective reactor tracking, as of May 2026, the Linglong one is still strictly categorized as under construction.
Okay, so no power yet.
Right, there is no verified grid connection date yet recorded.
So the engineering and non-nuclear testing are progressing. But until those electrons are physically synchronized to the grid, we keep it in the construction column. We stick to the verified facts.
We have to. It's
Yeah.
the only way to accurately measure the reality of the assembly line.
So what does this all mean? We've covered a staggering amount of ground today.
We really have.
We are looking at a system with 64 operating reactors and 36 more under active construction across 19 sites. They are executing complex logistical milestones week after week, whether it's Changjiang Unit 3 achieving the physics of first criticality, or Taipingling Unit 2 actually pushing megawatts to the grid.
Yay.
And they aren't just brute forcing older designs, they are deploying a highly calculated mix of generation through pressurized water reactors alongside cutting-edge generation THRV tech like the hybrid helium-cooled steam project at Seaway and the sodium-cooled fast reactors at Shapu.
Yeah.
All of this orchestrated to hit that 110 GeV goal by 2030.
Before we leave you with a final thought on what this unprecedented mobilization means for the future, I must provide a very clear, strict disclaimer regarding the institutional research we've explored today.
Please do.
This deep dive is for informational purposes only. It does not constitute investment advice, a recommendation, or an offer to buy or sell any security. Reactor status, construction timelines, and capacity figures are highly complex and subject to change. Furthermore, past performance and current status are not indicative of future results. Please conduct your own independent research and consult with qualified professionals before making any investment decisions.
Thank you. It is vital to maintain that rigorous context when we analyze industrial data of this magnitude.
It is. And this brings us to an important question, something for you to mull over after this discussion ends.
What's that?
We noted right at the beginning that the global average age of a nuclear reactor today is 32 years, while China's fleet averages under 12 years old.
Right, the age gap.
Now, fast forward 20 years into the future. As the rest of the world's legacy nuclear fleets inevitably begin to age out of their operational lifespans and face complex decommissioning processes, China will possess a massive, highly mature, and deeply experienced nuclear ecosystem, running heavily on proven Generation the Third and Generation the Fourth technologies.
Wow.
So the question is, how will this stark imbalance, not just in raw electrical capacity, but in operational experience, supply chain resilience, and heavy manufacturing capability, reshape the global energy landscape of the 2040s and 2050s?
When you look at an assembly line like this, you aren't just watching a 1,000-ton steel dome being lifted, you're watching the mechanical foundation of the future global energy market being forged. What stands out to you about this massive pipeline? Is it the sheer logistical orchestration, or perhaps the aggressive deployment of hybrid and fast reactor technologies? Keep exploring these sources, keep digging into the mechanics, and keep asking questions. We will be right here to help you unpack whatever comes next. Until then, keep diving deep.